Hey everybody, welcome back. So this video is about section 5.2. We're starting on chapter 5 this is our first video from chapter 5. So you might be wondering what happened to 5.1. Well, we're going to skip it because we don't really need it, okay? However, the binomial probability distribution, 5.2, is definitely a part of the curriculum at our school. And anything that we need from 5.1, we will kind of learn as we go through 5.2. So I've taught this course many times in person, so I've found that covering 5.1 isn't particularly helpful. So 5.2, binomial probability distributions. So these are a very common type of discrete probability distribution. And I know it's been a long time since we did chapter 1, but a discrete probability distribution essentially means that the number of possible outcomes is finite or countable, okay? And the focus of this section is the binomial probability distribution and methods for finding those probabilities. So make sure you've already gone through all of chapter 4, my videos, my homework, and quizzes from chapter 4 before you watch this video and try to do chapter 5, because you need to have a firm grasp of probability. Okay, so what is a binomial probability distribution? Like I said, it's a discrete probability distribution, which means that there are only a finite or countable number of possible outcomes. And it's a very common type of probability distribution from the real world. Now, I keep saying probability distribution, all that means is with a probability distribution, there are certain outcomes, and each outcome has a probability or a chance of occurring, okay? So in order to be a binomial probability distribution, there are a lot of conditions. So the procedure has to have a fixed number of trials, okay? And a trial would be a single observation. The second condition is the trials must be independent. So if you recall from section 4.2, if events are independent, that just means that the outcome of any individual event doesn't affect the probabilities of the other events. Here we're calling the events trials, but they're still events. So it's still the same thing that we learned when we were using the multiplication rule in section 4.2. Okay, the other two conditions that we have to make sure are true are that each trial must have all outcomes classified into exactly 2 categories. So why is that? Well, if you look at the word binomial, it has the word, at the beginning of the word, it has the prefix bi. So bi, like a bicycle, has 2 wheels. Binomial has exactly 2 categories of outcomes. And they refer to those categories as success or failure. So there are those 2 possible outcomes are either going to be success or failure. And because there are 2, just like a bicycle has 2 wheels, that's why it's called binomial. Okay, and then the last condition in order to be a binomial probability distribution is the probability of a success has to remain the same in all trials. And if you think about it, since we just said each trial has to be considered either a success or a failure, if the probability of a success remains the same, then that also means that the probability of not having a success remains the same. And not having a success is called a failure. Okay, so those are a lot of details. The only reason I'm talking about these is because it's important to understand what's going on with the binomial probability distributions. But when you're actually doing your homework, quizzes, and exam, you probably won't need these particular slides too much. I'm just describing how to label everything. So we're talking about two outcomes. We're calling one outcome a success and the other outcome a failure. All right. So don't take success and failure too literally. It doesn't mean that if you have a success as a trial, it doesn't mean that it's a good thing or a bad thing. And likewise, a failure doesn't necessarily mean a good thing or a bad thing. They're just names for the two possible outcomes. Okay. So here in our book, they use capital S to represent the event of a success in a single trial, and they use capital F to represent the event of a single failure in a single trial. Okay, so the notation that they use is here, the probability of a success in a single trial is equal to the lowercase letter p. Okay, so p represents the probability or the chance of a success in one single trial. Keep in mind that for a binomial probability distribution, we're going to have multiple trials. So for example, we might have 5 trials. Okay, but that probability of a success, we represent that with lowercase p, and that has to remain the same in every single trial. So if we have 5 trials, the chances of a success needs to remain the same in each trial. And then the chance of a failure, or the probability of a failure, is equal to 1 minus p. So that's 1 minus the probability of a success. And then they use the letter Q to represent 1 minus p. Okay, so Q equals 1 minus p. And like I said, since the chance of a success remains the same in all the trials, that means the chance of a failure, which is 1 minus the chance of a success, also has to remain the same in all the trials. So it has to remain the same. Okay? And then one other letter that we need to talk about, but it's a letter that we've seen quite a bit before, is N. So remember, throughout this course, whenever we use the letter N, that usually represents the number of data values in our sample, or in this case, N represents the fixed number of trials, so the total number of trials. Okay, but all of this stuff can be a little bit abstract. So I did want to write down a quick example, and then we'll return to the rest of this notation so that we can understand it a little better. So just a quick example that's not in the slides. So if you flip a coin, there are only 2 possible outcomes. Okay? So if you flip a fair coin, in other words, a coin that's not weighted more on one side or the other. So for example, if you just flip, say, a quarter, a United States quarter, that isn't particularly lopsided, so it's considered a fair coin. So if you flip a fair coin, then you're either going to have heads or tails. So each time you flip a coin, that would be a single trial. So that would be one single trial. And then in order to be a binomial probability distribution, let's say we flip a fair coin a certain number of times. So let's say we flip a fair coin a total of 4 times. Okay. This is an example of a binomial probability distribution. Because first of all, there are only 2 possible outcomes, heads or tails. And we just need to pick one of those outcomes to be a success and the other one to be a failure. So for example, if they asked us to, if they asked us whether this was a binomial probability distribution, we could say let flipping a heads be a success, and so that's talking about a single flip. So if you're flipping the coin once, heads would be considered a success, and then not having heads would be the other outcome, which would be tails. Then we could say tails let heads be a success and tails be a failure. So this is just a real quick example that I'm inventing on the spot here as an example of a binomial probability distribution. Because it's a fair coin, that would mean that the probability of a success, or P, is equal to 1/2 or 0.5. Okay, so we can see here that P would be 0.5. Okay, and because it's a fair coin, we're flipping it 4 times, but each time we flip it, it doesn't affect the chances of the other times we flip it. So each trial is independent. Okay, there are 4 trials. Each trial is independent. The chance of success, or the chance of heads on each trial, is 50% or 0.5. And then the chance of failure, Q, that's 1 minus P. Well, 1 minus 0.5 is also going to be 0.5. But that should make sense because just from the real world, everybody knows that you have a 50-50 chance. When they say a 50-50 chance, they mean a 50% chance of a success, which here we're calling heads a success, and then a 50% chance of a failure, so tails is a failure. Now, the number of trials is going to be labeled as n. So because we flip a fair coin 4 times, that means n equals 4. Okay? So this is an example of a binomial probability distribution. I'll just write PD, standing for probability distribution. So if we go ahead and go back to the slides real quick, we can see the reason this is a binomial probability distribution is condition number 1, the procedure has a total of 4 trials. Okay, that's the 4 times we're flipping the coin. Condition number 2, the trials are independent because flipping the coin each time doesn't affect the probabilities of the other times we flip the coin. So condition number 2 is satisfied. Condition number 3, well, there are only 2 outcomes, heads or tails, and here we're just deciding to let heads be a success and tails be a failure. So there are only 2 outcomes, and the probability of a success remains the same in all the trials. So as you can see, this example that we just did is definitely a binomial probability distribution. Okay, and then we're going to be doing more examples, but that's a good start, that one that I just came up with on the spot. So hopefully that helps to make it easier to understand. So let's continue to the rest of this notation here. So one thing we haven't talked about yet, we've talked about P, which is the probability of success. We've talked about Q, which is the probability of a failure on a single trial. We talked about N, which is the total number of trials. Well, the next thing that we haven't talked about is X. So X is a specific number of successes in our total number of N trials. So x can be any whole number between 0 and n inclusive. So for the example that I just erased, n was 4. So x could be 0, x could be 1, x could be 2, x could be 3, or x could be 4. So x is just going to represent a specific number of successes, and it has to be a whole number between 0 and n. It can never be larger than n. The reason we're learning about x is we're actually going to be calculating a probability in our homework, or multiple probabilities. And so they'll be asking us to find, for example, the probability of 2 successes. So then x would be 2. So if we flip a coin 4 times, what is the chance of flipping exactly 2 heads and exactly 2 tails? Well, in that case, we would have 2 successes, so x would be 2. And an important note, other textbooks and the binomial probability table in this week's module for our online class use the letter R instead of the letter X to represent the number of successes. Okay, so our book calls the number of successes X, but in the table that is easier to use than the one in our book that I'm including in this week's module actually uses the letter R instead of the letter X, but it still represents the number of successes. So just keep that in mind. Okay, so we already talked about the rest of this. So P is the probability of success in one of the trials. Q is the probability of failure in one of the trials. And then probability of X would be the probability of getting exactly X successes among the n trials. Now this is a little bit harder than it might seem to calculate. So there are a couple of ways we can do this. I'll show you both ways. The first way is with a formula, and then the other way would be to use a table. But the thing about the table is it doesn't always work, whereas the formula always does work. But I'll be going over both ways in this video. Okay, and I already mentioned this, but because it can be confusing to people, I'm going to mention it again. So, caution, the word success, as used here, is arbitrary, which means it doesn't mean a success or a failure in the traditional sense of the word. It's just in math, okay? It does not necessarily represent something good or something bad. Same thing with failure. I know success sounds like it's good and failure sounds like it's bad, but it just happens to be the words they use just to keep track of the 2 possible outcomes. And unfortunately, those words sound like they mean something more, and they don't. Okay, you could just as easily make success be tails and failure be heads, and it doesn't make any difference as long as you're clear with what you label to be a success and what you label to be a failure. They're just names for the 2 outcomes. Okay. So either of the 2 possible categories may be called the success S, as long as its probability is identified as P. So as long as you're consistent, you'll be good. The other word of caution is when using a binomial probability distribution, which is all that we're doing in this section, always be sure that X and P are consistent in the sense that they both refer to the same category being called a success. So even though it's kind of silly to call things a success and a failure because it sounds like it means something that it doesn't, the reason they use those words, I think, is just because they're easy to remember. Okay. And then as long as you're consistent, then you'll be okay. Okay. So you just have to decide what you're going to call a success, what you're going to call a failure. Stick to your guns through the rest of the problem, and you'll be good. Okay, so let's see another example besides the flipping a coin example. Okay, so this is an example on cash from our book. So when an adult smartphone owner is randomly selected with replacement, so when they say with replacement, they mean they randomly select someone from the sample, and then they place that person back into the pool. And then they randomly select another person, which means the same person could technically be selected multiple times, although that's probably unlikely. There is a 0.05 probability, or a 5% chance, that this person is cashless. So they never carries cash. That person never carries cash. So this was based on a U.S. bank survey of over 2003 adult smartphone owners in the U.S. But this was just a particular survey, and this was also at the time the book was written. So that's just for the people in this particular survey. They found that there was a 5% probability, or 0.05 chance. So let's say we want to find the probability that among 10 randomly selected adults from this group of 2003 adult smartphone owners, exactly 2 of them are cashless. All right, so for part A, their first question is, does this procedure result in a binomial distribution? So if you want to, you could pause this video real quick, think about that, and then unpause it once you've decided. So you're going to need to check all 4 conditions. Okay, the answer is yes. It does result in a binomial probability distribution. Let's see why. So, first of all, the number of trials is fixed. They're saying that there are 10 trials here. Why are there 10 trials? Well, here they're asking us if we randomly select 10 adults. Well, when we're selecting them at random, each person that we select and their response on the survey represents a single trial. So there are 10 trials, and that's a fixed number, so that satisfies the first condition. The second condition is also satisfied. So the 10 trials are independent because the probability of any random adult smartphone owner being cashless is not affected by the results from the other randomly selected adults. Because like we said, we're selecting someone at random, and then we're putting them back into the pool. So that's called with replacement, because we're replacing them back into the pool. And technically the same person could even be picked multiple times. So the chances for each trial remain the same because it's the exact same group of people. Okay, so that's satisfied. The third condition, each of the 10 trials has 2 categories of outcomes. So the selected person is either cashless or not. So it's up to us whether we want to say cashless is a success or not cashless is a success, as long as we're consistent and we read what they ask us in the next question. It doesn't matter what you label as a success or a failure, as long as you're consistent. And here we can see there's only 2 possible outcomes, which are cashless or not cashless. So that's satisfied. And then the last condition, for each randomly selected adult smartphone owner, there is a 5% probability that this person is cashless. And the thing is, because we're gathering each person from the same group, and we're also putting the person back into the pool, the probability remains the same for each of the 10 selected people. Okay? So for example, if we say being cashless is a success and not being cashless is a failure, just arbitrarily, there's a 5% chance of a success, and that chance of a success does not change. So it satisfies the 4th condition. Okay, but when you're doing your homework, most of the problems are going to be a binomial distribution. I just wanted to point that out. And the reason is, if it's not a binomial probability distribution, then we can't really do the math for it, which is why there's not that many homework problems where it's not a binomial probability distribution, right? Because we're here to learn the math, really. Okay, so let's move on to part B. So for part B, if this procedure does result in a binomial distribution, identify the values of n, x, p, and q. Okay, so on the example that I invented on flipping a coin, we already talked about how to find n, p, and q. But in this example, we can also figure out what x is. So let's go ahead and do that. All right, so let's start with n. So n needs to represent the total number of trials, right? So n doesn't actually represent the 2003 adult smartphone owners, even though you might be tempted to think that it was that. That's actually our sample size, and normally in some of the other problems that we've done earlier in the course, I know the sample size is usually n, but here n would actually be the 10 randomly selected adults because n represents the total number of trials, and there were a total of 10 trials. Okay, so here we can see that n equals 10. Okay, so n equals 10, and then what about x? X represents the number of successes that we want, and they're asking us if we let, we'll just go ahead and let being cashless be a success. Well, if exactly 2 of them are cashless, that's what we're trying to find the probability of, that means that x equals 2. Okay? So x is the same as the exact number of successes that we're trying to find the probability of. And x always has to be between 0 and n. So here x has to be between 0 and 10. And here, because they're asking us, well, we want to find the chance that exactly 2 of them are cashless, x equals 2. And we're calling being cashless a success just because it makes sense with the way they're asking us for the problem. So when they're asking you to find the chance that exactly 2 of them are cashless, that just makes sense that being cashless would be called a success. All right, and then P has to represent the probability of a success on a single trial. Okay, so on a single trial, they said that there is a 0.05 probability that a person is cashless. So that means we write P equals 0.05. I'm sorry, I misspoke. I don't know why I said that, but it's a 0.05, not 0.5. All right, and then the only part of this problem that involves any math is Q. So how do you find Q? Well, we said that Q is the probability of a failure. So that's actually from the complement rule. We know that Q equals 1 minus P. That's one of the worst Q's I've ever written. Let me just write that one more time. Okay, so Q equals 1 minus P. So 1 minus P here is going to be 1 minus 0.05. All right, and if you can't do that in your head, you're welcome to plug it into your calculator. So 1 minus 0.05 is 0.95. Okay, so that's 0.95 for Q. Okay, so here we've got the information they asked for. N is 10, X is 2, P is 0.05. We can always get Q by doing 1 minus P because the probability of a failure has to be 1 minus the probability of a success using the complement rule that we learned in section 4.2. So that's all the information that they asked for. Okay, so then in the book, you can see that they said the same thing I just did. So we're going to skip those next 2 slides. I just like to write stuff out as I'm describing it. Okay, the only thing you notice here, though, is that you do have to be consistent. And when you're reading the problem, just choose a success to be what they're asking you to find a certain number of. So here, if they asked us to find exactly 2 of them are cashless, obviously we want to make cashless being a success and not being cashless be a failure, because that's the wording of the problem. Okay, cool. I know this is kind of repetitive, but consistent notation. Again, it is very important to be sure that X and P both refer to the same concept of success. In this example, we use X to count the number of people who are cashless, so P must be the probability that the selected person is cashless. Therefore, X and P use the same concept of success, being cashless. Okay, already said that. All right. So while I erase all this, let's take a look at this next slide. So in the example we just did, we were using replacement, which means that we would select a person at random, and then we would put them back in the pool. So we would replace them back into the pool of people, and then we would select the next person at random. However, the point of this slide is it turns out that you can use this. So it says a 5% guideline for cumbersome calculations. So when sampling without replacement, in other words, for example, if we're doing a problem where we're randomly selecting people, without replacement would mean we select the first person and then we don't put them back into the pool of people. And then so the pool is missing that first person, and then we select the second person at random, and so forth. So that's what without replacement means. So we're not replacing them into the pool. It turns out that we can still treat each of those trials as independent events as long as the sample size, so the size of our sample, is no more than 5% of the size of the population. Okay? So this is called the 5% guideline for cumbersome calculations. Cumbersome means tedious. Okay? So what they're saying is you can treat the selections as being independent even though they are actually dependent. And the reason you can do that is if your sample is small enough, the chance of if you take one person out and you don't put them back, if you had put them back, your sample size would be small enough that you would be extremely unlikely to choose the same person again anyway. So because you'd be extremely unlikely to choose the same person multiple times in each trial, it doesn't really end up affecting the numbers very much, is essentially, what's going on. So hopefully that makes a little bit of sense. Anyway, even if it doesn't make sense to you and you don't understand it, the thing is, you could just look at your sample size. If it's 5% or less, then you can just treat the selections as being independent. So that does show up a little bit on your homework. And so, if we look at, for example, if our sample size was only, let's say we had n equals 13, and then let's say that those 13 trials are actually taken out of a population that's much larger, then we would be able to use this rule. So say n equals 13, and then the population size from which we drew these 13 trials could be, I don't know, let's just say 50,000. Well, then how do we know we can use this rule? Well, if our population size would be 50,000 people, let's say it's a certain town that had 50,000 people, that would be our population. If I do 50,000 on my calculator, and then times 5%. Remember, 5% is the same as 0.05 as a decimal. 50,000 times 0.05 would be 2,500. Okay, so in other words, 5% of the population would be 50,000 times 0.05. 50,000 times 0.05. And that's 2,500. So here, if n is 13, the size of our sample, or the number of trials, is clearly actually less than 5%, right? Because 5% of the population is 2,500 people, and we're only at 13. So this would be an example of where the 5% guideline for cumbersome calculations tells us that we can just treat these selections as being independent, even if, as we're drawing these 13 people for our trials, even if we're not putting them back. So even if we're doing them without replacement. Okay? So that's just a helpful thing to know. You won't necessarily have to use it a whole lot on your homework, but it does show up, so that's why I'm talking about it. Okay, so I'm going to go ahead and erase this while we go on to the next slide. So we haven't done a whole lot of math today in this video. So let's go ahead and get to the math part of this section. It's a big section, and you know, this is the fun part, if you like math. Okay, so method 1, if you're trying to find a probability, you can use this binomial probability formula. Okay, so we already talked about what it means to be a binomial probability distribution. We've already learned how to identify these letters. So this formula looks quite intimidating. I know it has a lot going on, but it's saying that the probability of x successes equals n factorial over n minus x factorial times x factorial. I do want to point out that this right here is just the combinations formula. So if you're good at doing combinations, you can either use this formula, or most modern calculators have NCX or NCR. Remember, some other books and some calculators use R instead of X. So I do want to point that out just right off the bat, because looking at this right here, it does look a bit complicated, but this first part of the formula is just the same as NCX. That is NCX. Okay, so that's just the combination of n is the number of trials and x is the number of successes that we're trying to find the probability of. Okay, and then for the rest of this formula, the rest isn't too bad. So the next thing we have is times p to the x. So remember, the p represents the probability of a success on a single trial. X is the number of successes. So that's a power there that you can just type into your calculator, times q to the n minus x. So the thing is, n minus x, all you're going to have to do is, in your head or on your calculator, you just do n minus x, and then q is the probability of your failure, which you hopefully have already calculated when you're doing your homework using the formula q equals 1 minus p. So on the one hand, it looks like a lot, it looks complicated, but if you look at the individual parts of this formula, it's not too bad. But obviously, it's good to already know how to do combinations, because, for example, if you can just do NCR or NCX on your calculator, that can make this part take a lot less time. okay, which we talked about in detail in section 4.4. Okay, and we've already talked about these letters. So let's go on to the next slide. So here's the rationale or the reason this binomial probability formula that I was just talking about, why it makes sense. Okay, so here, first of all, we see that the probability of x successes is equal to n factorial over x minus n factorial times x factorial. As we just said, that's the same as ncx. So that first part of a formula, the reason this part makes sense is it's counting the number of outcomes with exactly x successes among n trials, because the order doesn't really matter. So the order in which you have your successes doesn't matter because they're asking us to find the probability of x successes in n trials. Well, if you have, for example, if you have 10 trials and you want the probability of 2 successes, it doesn't make any difference whether the first 2 trials were successes, or the third trial and the 5th trial were a success, or the last 2 trials were successes. All that matters is that after all the trials are done, exactly 2 of them are successes out of the 10 trials. So hopefully that makes sense. So we're using combinations here for this part of the formula because with combinations, recall, order does not matter. All right. Now over here, the rest of the formula is representing the probability of x successes among n trials for any one particular order. So the reason they're multiplying this times that is together, the order doesn't matter. And so when you multiply them, the order doesn't matter because of the combinations part of the formula. And then this over here, the p to the x and times the q to the n minus x, tells you the probability of x successes among n trials for any one particular order. Okay. So this includes the order, but then the combinations formula sort of gets rid of the order, roughly speaking. Might be a little more complicated than that, but this is how they describe it in the book. Anyway, the order doesn't matter, and that's why we're doing combinations. Okay, so if we go back to our cash problem, let's see if we can go ahead and calculate a probability. So given that there is a 0.05 probability that a randomly selected adult smartphone owner is cashless, use the binomial probability formula, that scary formula that we just saw, to calculate the probability that when 10 adults are randomly selected, exactly 2 of them are cashless. For this same problem, we already identified that n was 10 trials, x was the 2 successes that we want, p was 0.05, and then q was 1 minus p, which was 0.95. Okay. So as you've probably noticed, I like to write out the math, even though it's also on the slides. It's just more fun for me to teach it that way. I don't know if it's more fun for you to watch because the videos take longer, but you know, it's how I teach. So looking at this formula, I'm going to rewrite it in a simpler way. So like I said, this first part of the formula is the same as NCX. So if we use this formula, we can see that since x is 2, we're trying to find the probability of 2 successes. So the probability of 2 successes is going to equal, remember this here is NCX. So this first part of the formula is just NCX. So rather than using all the complicated factorial notation, I'm just going to write NCX, and in this problem, we see that n is 10. So that's just going to be 10C2, okay, 10C2, times p to the x. Well, we know that p is 0.05 and x is 2. So we're going to be times 0.05 is P, and then X, we said was 2, times Q to the N minus X. Well, Q is 0.95, all right? So Q to the N minus X is going to be 0.95 to the, well, what's N minus X? Well, you could write it out, but most people could just do it in their head. 10 minus 2 is 8. So it's going to be 0.95 to the 8. Oops, did not mean to go that slide yet. Okay, so hopefully that makes some sense. So probability of exactly 2 successes equals 10C2 times P to the X, so 0.05 to the 2, times Q to the N minus X, 0.95 to the 8. Now, how you do this on your calculator is really up to you. Because I don't make people have a specific calculator, I have to be very general in the way I teach my videos. I know some instructors make you get a particular calculator, but I don't do that. So hopefully you already know how to do 10C2 from watching my other videos because I went over it in details. But for example, on my calculator, I can do 10C2 by just typing 10, which is N, and then I press PRB, and then I go to NCR. Well, on my calculator, they call it NCR instead of NCX, but it's still combinations. It's still this formula. So it's 10 NCR 2, and then I press enter, and that gives me 45. Okay, so 10C2 is 45. And of course, if your calculator for some reason doesn't have NCX or NCR, you can also do it with factorials the way we did before. But I don't want to take up more time in this video doing that because I did multiple examples of that in section 4.4. Well, I don't know if I did multiple examples, but I know I did at least one example of combinations, and I did other examples where we were canceling out factorials. So basically, you would just do 10 times 9 times 8 factorial. Then you would cross out the 8 factorial, so you'd have 10 times 9 over 2 factorial, which would be 90 over 2, which is also 45. So any way you want to do the combinations is up to you. Okay, 0.05 squared, I can just type that into my calculator. On my particular calculator, the exponent button looks like an up arrow, sort of. So I just do 0.05, I press the exponent button, and then I press 2. And that tells me that 0.05 squared is actually 0.0025. 0.0025. Okay, and then we also have times 0.95 to the 8. So using the same exponent button, I can do 0.95 to the 8th power. Unfortunately, this number has a lot more digits, and I don't want to really round until the end, so I'm going to write out a bunch of digits. So here, for 0.95 to the 8, I'm going to go ahead and write out as many digits as I can. So 0.663420. That should be enough digits. So I'm just writing out a lot of digits so that I don't have what's called a rounding error. You don't want to round the individual parts of a formula. You only want to round your final answer. Okay, so now if I go ahead and multiply these three numbers, on my calculator I got 45 times 0.0025 times 0.663420. And that gives the probability of exactly 2 of those 10 people being cashless. And that's that gave me 0.07463. And if we follow the 3 significant digits, that rounds to 0.0746. Okay, and there's no room to write it down here, so I'll just write it up here. So for the probability, I have 0.0746. Okay, so that's not too bad. And I did also want to point out that with a calculator, with a lot of modern calculators, you don't necessarily have to write it out as 3 separate parts like I did here and then multiply each part. So to save time, if you become skilled with your calculator, one thing you could do is you could just put parentheses around the 10C2. Okay, and then if you type it in, if you type all that in properly on your calculator, you may be able to just type in all of this all at once and then get to the 0.0746 all in one step without having to write 45 times 0.0025 times this. But that's really up to you, and you're practicing on your individual calculator. Okay, cool. So let's return to the slides while I erase this. So as you can see on the slides and in our book, they got the same exact answer as we did, so 0.0746, and they rounded to 3 significant digits, as we usually do for probabilities unless they tell us otherwise when we're entering in our answer. Okay, and if you're wondering what that means, you can always convert it to a percentage. So that would be the same as a 7.46% chance that out of 10 randomly selected adults in that survey, exactly 2 of them said that they were cashless. Okay, cool. So the only problem with this formula is even if you're really good with your calculator, it can take quite a while to type it in. I realize that. And if you make one little mistake typing it in, when you're doing your homework, you may find that you actually get the wrong answer. So on some of your homework problems, you're sort of going to be forced to use the formula because you can't use a table for certain problems. So that's why we learned the formula. So you always have this formula to fall back on. But it turns out that it's easier to use a table in certain situations as long as P, Q, N, and R actually show up in the table. Okay, so I put a table in this week's module, the binomial probability table. It's included in this week's module, and it lists binomial probabilities for select values of N and P. Now, if you're using our textbook or our e-text on MyMathLab, you may be using table A1 in Appendix A. However, I wasn't able to get this table to put in our module, so I got another binomial probability table that's easier to read, and it also has more numbers, so it's actually better than table A1 in the appendix. So if you want to use table A1 in the appendix, you can, and when you're doing your homework, quiz, and exam on some of these problems, they will actually include a table. You can click on it while you're doing your problem. But for most of us, I would recommend that you just download the binomial probability table included in this week's module, and then you open it up and use that, because that's better than, in my opinion, better than table A1 in Appendix A. Okay, anyway, it lists binomial probabilities for select values of N and P. Table A1 cannot be used if N is greater than 8, or if the probability P is not one of the 13 values included in the table. So I'm going to show you right now the table that we have. It's not table A1 in Appendix A from our book, but I'm calling it the binomial probability table in this week's module. So here it is. Let me zoom in here so we can look at it. This is actually, it's called Table 4, Binomial Probability Table, or Binomial Probability Distribution. And like I said, they're using R instead of X for the number of successes, but it's still the same formula. It's still NCR, P to the R, Q to the N minus R. Anyway, we'll go back to this table, but you'll notice that each of these columns is representing a certain probability of success P. So for example, this column right here would represent a probability of success, which would be 0.45. So for example, your probability of success is 0.45, you would be looking at this column. And then if you look on the left side, each of these rows is labeled. So here, this represents N. So if we had, for example, 5 trials, R would be the number of successes. So if we had 5 trials, 2 successes, and then 0.45 probability of success, we would just go down here and look where the 2 and the 0.45 meet, and that would just tell us that there's exactly a probability of 0.337. And the nice thing about that is we didn't have to do any math, really. We just had to look it up in the table. But like I said, do notice that this is only going to work for certain values of P and also certain values of N. On this table, N only goes to 11. And then the one in our book, N only goes to 7, I believe, or 8, maybe. This one happens to go to N equals 11, though. But for N equals 11, it doesn't even include all of them at the bottom. So you can use these tables if you'd like to, or you could just always use the formula. But the nice thing about the table is if you have to look up multiple probabilities, and it's in the table, it could save you a lot of time because you could just add up the multiple probabilities and it would just be a heck of a lot less work. Okay, so let me go back to the slides. Okay, and then I wanted to point out here what we're going to be doing. So to use the table, we must first locate N and the desired corresponding value of X, or in the case of the binomial probability table that I just showed you, instead of X, they would call it R. At this stage, one row of numbers should be isolated. Now align that row with the desired probability of P by using the column across the top. The isolated number represents the desired probability. A very small probability, such as 0.000064, in other words, if you have a lot of zeros before your first non-zero digit, is indicated by 0 with a plus after it. The only reason I'm mentioning this is that I think in one of your homework problems, they might actually ask you what this represents. And all you have to do is choose the option that says it represents a very small probability. Okay. And that's for table A1, not for the one that we have in our module. Okay, but table A1 is the one they're using on my math lab, so if you prefer to use that one, you're welcome to. Okay, so let's see this whole table business applied to an example. So example on veggies. Based on a Gallup poll, 5% of US adults are vegetarians. If we randomly select 5 adults, find the following probabilities by using table A1. So I will show you table A1, which is on the slides, and then I will also show you the table, it was table 4, which was the one that we just were taking a look at. So I'll show you both on this video. Okay, so let's take a look at this. Oops, wrong button. Okay, so part A, we want to find the probability that exactly 2 of the 5 adults are vegetarians. So this video is getting pretty long, so I'm going to try to speed things up a little bit here. So let's just go ahead and look at, they've done this on the slides for us. So looking at part A, for table A1, the excerpt from the table shows that when N equals 5 and P equals 0.05, right, because we said 5% of US adults are vegetarians, that means 5% is the same as 0.05 as a decimal. You move the decimal 2 places to the left. So the probability of success is 0.05. P equals 0.05. The probability for X equals 2 successes out of N equals 5 trials. Well, if you're using table A1, you would just look for For P on the top here, so where P equals 0.05, that would be your column. And then on the left side, you look for N is 5, and then we said that X was 2. So here's 2. So right there, this right here, actually let me use this. That's a little, we got 0.021. So where X is 2, and P is 0.05, and N is 5, where all those meet is at 0.021. So without even having to use a formula, we have the probability of exactly 2 successes equals 0.021. Okay, and then we can do the same thing with the table that we were just, the one that's in our module for this week. Let me just show you that real quick, if it's still open here. Okay, so here, I need to change the view here. Let me fix that real quick. Okay, so for N is 5. Here, instead of X, we have R. So R is 2. So if N is 5, R is 2, then we go over here, and we said that P was actually 0.05, so I went way too far. So P was 0.05, which is that right there. And you can see we get the same value. So this is it right here. Ooh, that's hard to write that small, but we can see that 0.021 is what we wanted. Okay, so same number, 0.021. Okay, so regardless of which table you're using, they work basically the same way. It's just the one on the module has more numbers, so you'll be able to use it better. Just remember that R is the same as X. Okay, so let's go ahead and go back to the slides. So with the slides, that's table A2. Sorry, A1. I don't know why I said A2. A1. Okay, and then let's see their next question. So the next question they ask us is the probability that there are fewer than 3 vegetarians. So this is a little bit harder. And if we did use the binomial probability formula, this would be very tedious. Let me explain to you why. So when they say fewer than 3 vegetarians for our number of successes, well, what does that mean? So probability that we have fewer is the same as less than. Fewer than 3. Well, here we're calling a success being a vegetarian, not to be taken literally. Probability of fewer than 3 is the same as the probability of any number that is less than 3. So 2 is less than 3, 1 is less than 3, and 0 is less than 3. And remember, your number of successes has to be a whole number. It can't be a fraction or a decimal. So the probability of fewer than 3 is the same as the probability of a 2. 2 of them are vegetarians, or 1 of them is a vegetarian, or 0 of them, none of them are vegetarians. And remember, with the word or, as long as the events are disjoint, which means they don't have any overlap, in other words, they both can't occur at the same time, the word or is actually just the same as addition. So here, we would be using the addition rule from section 4.2. So we just replace or with plus. Let's see that. Wrong button. Okay. So probability of 2 or 1 or 0 is going to be the same as P of 2 plus P of 1 plus P of 0. Now, like I said, you could technically do any of these problems using the binomial probability formula, but a table would be way quicker, because here we actually have to look up 2 successes, 1 success, and 0 successes, and then we have to add up those 3 probabilities. If we were using the probability formula, we would have to calculate each of these by typing each of these into our calculator, which takes a long time, and then we would have to add up all those probabilities without rounding, so that can be very tedious. So this is an example of where the table can be a lot faster. So let's see the table in action here. So if you're using table A1, like I just said, probability of 0 or 1 or 2, or just means add, essentially, because these are disjoint events. So that's P of 0 plus P of 1 plus P of 2. So you can look up each of those, P of 0, P of 1, and P of 2 in the table. They don't have it, unfortunately, on the slides. I forgot that they didn't have it there. So let's just go ahead and look these up. So P of 0, P of 1, or P of 2. So if we're using table A1, that would mean X is 0, X is 1, or X is 2. But if you're using the table that we're looking at right now, that would mean R is 0, R is 1, or R is 2. So let's take a look at this. So because there were 5 trials, we're looking at N is 5. And then we said for this particular problem, there was a 5% chance or a 0.05 probability that a person was a vegetarian, at least in this study. So looking at this column, and 5 is the row, we can look up the 3 probabilities that they got. So P of 0 plus P of 1 plus P of 2. So that's going to be, this one, 0.774 plus 0.204 plus 0.021. So we can just easily look up those 3 probabilities right there. And then because they're using the word or, we just add these up on our calculator, and that enables us to very quickly and efficiently get to the result. Okay, so that's really much quicker than the formula when you have to look up multiple probabilities. Okay, so as you can see, they got the same numbers here, so 0.774 plus 0.204 plus 0.021. And then if you add those up on your calculator, you're going to get 0.999. And yes, we could have done each of those with the binomial probability formula. So x would be 0 here, x would be 1 there, and x would be 2 there. But we would have to calculate each of those by typing in the long formula. So it would be 5c0, p to the x, q to the n minus x, and then the same thing for 1, and then the same thing for 2. Then we would have to add them up. That's a lot of extra work. So table definitely helps here. Okay? So I hope that this video was helpful, as always. And then I believe that was it. Yeah, so that is the end of the slides for this video. Thanks for watching. I will see you guys next time.